Okay, in this and the next video, I think we're going to finish up tolerances of orientation. I do want you to continue to read through the handout and look at some of the other examples. Some of them take a little bit of thought, but again, I think the illustrations are very good, especially if you read and understand the means this portion of this. So I don't want to go through all of these examples. Because we really do need to move on, given that we only have 8 weeks. What I do want to do in this video is highlight a couple of the sort of fancy symbols that we can use to take better control of the tolerance zone and adjust it based on where we want it and how we want it. And then really that is, again, the goal of GD&T, is to give us a great toolbox for defining the tolerance zone and adjusting it if we need to. Okay, I'm going to start by directing you in your handout on orientation to figure 611. And what you're going to see here is a pretty conventional metric tapped hole. It's an M10 by inch or 1.5 millimeter. And that is the class of the thread. So this is 10 millimeters, roughly a 3/8 tapped hole, so it's not real big. And what the point of this example is to show you that even though we have some default assumptions about the tolerance zone, and one of the key assumptions that we always make is, where is the tolerance zone? The tolerance zone, unless otherwise specified, is or begins where the feature begins, ends where the feature ends. Sometimes it's not really that easy to determine where that is, but that is the rule. But there are instances where we want to violate that rule, and again, that's perfectly fine as long as we specify where the tolerance zone is going to be. The default tells us that it's always at the beginning and end of the feature. Sometimes though, we do want to pick up that tolerance zone, define its size like always, define its shape like always, but pick it up and put it somewhere else. And this is an example of where we would do that. Okay, so if we look at this feature control frame, you're going to see it looks a little crowded in the tolerance zone block. We have a datum surface A, just a flat surface that the hole is tapped into. And what the control is perpendicularity. So they're trying to maintain the perpendicularity of that tapped hole to the surface that it was tapped in. Obviously, a very common concern is that we don't want our holes tapped off at angles. So we want the perpendicularity of that tapped hole to be within a certain amount. The problem with tapped holes, just as a little aside, is that tapped holes have a lot of features. They have a drilled hole, they have a minor diameter, they have a major diameter, they have a pitch diameter, and the question is, what axis, which one of those features are we actually controlling? Well, the standard does say, sort of in the small print, that when we're dealing with a tapped hole, we should be as a default, the feature that we are controlling is the pitch diameter. Okay, now the pitch diameter, if you'll remember from blueprint reading, is sort of halfway between the minor diameter and the major diameter. It's just sort of an arbitrary analytical point. But we do have tools, expanding plugs, thread gauges, that sort of thing, that actually do measure that and orient to that feature. So it's a useful enough feature, and it's a good starting point for orienting the tapped hole. So in this case, when we talk about the center line of this feature, of this tapped hole, we're talking about the center line of just one feature on this tapped hole, and that is the pitch diameter, which should be sort of halfway between the minor and the major. Okay, now we're going to try to unravel or unpack this tolerance zone information We know that we need to be perpendicular to datum A within 0.3 millimeters. It is a diametral tolerance zone, so we know it's going to be a cylinder that's 0.3 in diameter. Under normal circumstances, that cylinder would be start here and end right here, where the feature starts and ends. Again, the feature doesn't go this far, so realistically, our tolerance zone would start where the thread starts and end where the thread ends. And it would be 0.3 in diameter, and that would be that. And that tolerance zone then would be there. In this case, though, the addition of these two symbols are going to change that a little bit. One is the maximum material condition modifier, which we've talked about in a previous video. We know that this 0.3 diameter tolerance zone only applies when the feature is at its maximum material condition. In other words, when the pitch diameter is at its smallest, that means the thread is at its smallest or tightest. And now we're up against it in terms of, well, what is the tolerance for that pitch diameter? That's not on the drawing. If you need to know that, and in this case, if you're trying to evaluate whether you're meeting that requirement, you'll have to go to Machiner's Handbook or the internet or something, and there will be a published tolerance for the pitch diameter. There'll be a minimum material condition, or at least material condition, and a maximum material condition number there, and you can evaluate the material condition in terms of the tolerance zone. Okay, so that's a kind of a complicated thing, but it follows all the same rules. Maximum material condition, the tolerance zone is diameter 0.3. As the pitch diameter gets larger and larger within its tolerance, we add it millimeter by millimeter to that tolerance zone. So the tolerance zone gets bigger and bigger the looser the thread gets. All makes sense? Now, we've got to deal with this portion of it, and this is where things are really a little more complicated, and it's not like this is a real common practice, but it is available to you as a tool. If you look back at your table of symbols that I gave you, that P stands for projected tolerance zone, or projected. And this is the symbol or the tool that we're going to use to adjust where the tolerance zone is and where it starts and ends. This is the unless otherwise specified portion of that. Unless otherwise specified, it is here. Well, we're going to specify otherwise. We're going to project that tolerance zone. In other words, we're going to pick it up and put it somewhere else. Now, where is that somewhere else? We're going to project it completely off the part, or completely away from the feature, and we're going to start the tolerance zone where it would normally end. So we're going to pick up this orange tolerance zone and project it straight upward, still perpendicular to the datum, still 0.3 diameter, and we're going to just lift it up bodily and put it over here. How far? We've established where it starts. Now it's going to start where it originally ended. And we are going to project it 14 millimeters up from this surface. So now the tolerance zone starts where the feature ends and ends at 14 millimeters above it. It's really pretty simple, or at least in terms of interpreting the GD&T portion of it, it's fairly simple. It's a kind of a hard thing to actually design a feature and know where that tolerance zone should be. That's why you don't see it very often, but it does have a practical purpose, is that whatever goes in this tapped hole is actually what we're more concerned about. We don't really care about the tapped hole so much. What we're concerned about is the bolt that's going to go into here. Now, if that's a fairly long bolt, a little bit of angularity of this tapped hole is going to project that bolt off into space here somewhere. So we're not really concerned about where the tapped hole is. We're concerned about where the center line of the fastener is at some distance away from the surface. And this is what this projected tolerance zone symbol gives us, that control to actually worry more about the center line of the fastener that's going to be put in there than the center line of the tapped hole. Now obviously they're somewhat related, but there is clearance. So we control the center line at some distance away from the feature where it's much more useful. And that will guarantee that when we go to bolt, whatever we're going to bolt onto that, let's picture a stud on an engine, and you're going to bolt the heads onto an engine, and if those tapped holes are off at an angle, you're not going to be able to fit the head on over the studs. So again, this is a practical consideration. Again, you don't see it very often. It's a special case where you might have a close fit. You'll often see this more often than the tapped hole. You'll see it on a reamed hole where you have a pin, and that pin is used to locate some other feature. So again, this isn't a perfect example for a couple reasons. One is that you have to know that you're dealing with the pitch diameter in terms of the feature. The actual feature is that pitch diameter, not the major and not the minor. You have to know that it is the pitch diameter. You have to know what the tolerance is for that pitch diameter. That tolerance is almost never given on the drawing. It's actually in this portion of the specification. So you have to look up that class of thread, and it will tell you what the limits of size are on the pitch diameter of that thread. So again, sounds complicated, looks a little weird, but it is a practical thing, and you can evaluate it on that basis. Now again, this gives you the ability to project the feature. This gives you the ability to project it off to whatever distance you want. If you really wanted to do this and you really didn't want to have to deal with all of that, you can, let's say I want the tolerance zone to start 10 millimeters and project up to 24 millimeters. There's no easy way to do that with the projection symbol. The projection symbol picks up the tolerance zone and puts it where it originally began. If you need to do something really fancy like this, and again, I don't know what scenario would lead you to do that, but if you wanted to do it, you can do it just as I've drawn it. You can draw the tolerance zone, you can dimension the tolerance zone with basic dimensions. And normally there would be a note written that says noted tolerance zone is projected 10 millimeters to 24 millimeters up from the surface. The location of the pitch diameter of that thread is to be evaluated within that tolerance zone. That's why we have GD&T feature control frame, so we can avoid all of that verbiage, all the drawing. But again, you can do it. No rule says that you have to control in the feature control frame. You're certainly free to draw whatever you need to draw, write whatever you need to write, and make sure that it's clear enough that who's ever looking at it really understands it. So this sort of is the example of really taking control of the tolerance zone, putting it where we want it, and allowing its size to adjust at the same time with the maximum material condition modifier. Okay, so what I want to cover on the rest of this video is another symbol that again is fairly rare, but I want you to be aware of it, and this is in figure 618. And we have a simple illustration here of a little block with a datum and a parallelism. Always have to have the datum reference because this is an orientation control. So what is this saying? They want this surface to be parallel to the datum A surface within 1/10 of a millimeter. And so that would mean that you would have a .1 millimeter wide tolerance zone, and that surface then could be tipped however it needs to be. But suppose that surface, it looks nice and flat, but suppose this is a casting or some other feature that has a really rough surface. At that point, with just this control now, we don't have any form control, that surface could actually be like this. Okay, so we've got a real gnarly surface. Now if you kind of look at it, you'd say, well, it looks sort of like that surface. Even though it's really rough, its flatness isn't real good, but its parallelism is pretty good. It looks pretty good. It looks like the average, if we draw an average line through here, it looks like it would meet that parallelism requirement. What the symbol here, the T symbol, means is tangent plane. And what that tells the person who's going to inspect this for parallelism is, because this surface isn't really very flat, and doesn't need to be really flat, but we do want it to be pretty parallel to this surface, is we can take a secondary surface or a fixture of some sort and establish a tangent plane that is flat, and we'll set it on that rough surface. Okay, so if you picture taking a piece of sheet metal on a cast surface and setting it down, now you can evaluate it. If you run an indicator across this and try to check it for parallelism, you're going to find that it's so rough that you can't, it'll always violate that tolerance zone. In this case now, with the tangent plane, we can evaluate it with an indicator and determine that it is actually very parallel to datum surface A. So what it does is sidesteps a surface that doesn't have good form control, doesn't have good flatness. It allows us to take an auxiliary surface, usually a parallel ground plate or something like that, and evaluate its orientation without any regard to its form. Okay, so there are a couple new symbols that I want you to be familiar with and recognize what they stand for and why they're there. Okay, I'm going to terminate this video. Next video here, we're going to talk about just one more aspect of orientation, and then we're going to leave this topic and move on to profile.